Okay, I started recording. Okay, for this week, we're going over binary search trees, traversals, and you guys won't really need to know rotations for your class, but it's good to know about balance trees and how like they rotate to like balance them out as well. So it's gonna be similar to just the lab. I'm gonna do like the lab, like through it very quickly, and then I will show you a couple of methods, and then it's pretty simple like that. And I'll try to elaborate on like certain things as well. So so we have a binary search tree. That's a type of tree, right? So a tree doesn't have to be a binary search tree, but a binary search tree is the type of tree. And then so the unique thing about binary search tree is that it has two children. So we always at most have two children. That means it can have one, it can have zero, but it cannot have more than two. And then usually how it works is it's organized in a way that the left child is less than some sort of metric, like maybe like numbers is less than, but there has to be some sort of metric to organize and sort the binary search tree. So when we talk about numbers, we can just like so left child is less than the parent, and then the right child is greater than the parent. So right here, you see 5 is less than 7, and 7 is less than 9. So the left child is the smallest, and the right child is the bigger one. And the reason why we need a metric is because the point of this tree is that it's very efficient for sorting. And then we have so kind of like basic structure is the root node is always the top node. And then the children, so these nodes are children of the root node. So this is the parent, and these would be the children, and this is like a just general structure. And then so the internal nodes are nodes that are not leaf nodes. So leaf nodes are so that means we have to know what a leaf node is. So leaf node is a node that does not have any children at all. So here we would see that 5 is a leaf node, 8 is a leaf node, 10 is a leaf node, and 13 is a leaf node. That makes sense. So then anything else that's not a leaf node would be this part. And then that would be our internal nodes. So leaf nodes are also known as external nodes. And then the other ones will be internal nodes. Okay. And then so if you realize that, then internal plus external is usually like all the total of all your nodes. And then for parent, grandparent, anything like ancestor is just like anything that can go up the tree. So this would be the parent, this would be the 11 would be the grandparent of 5. So I think that's pretty simple. And the other two things that I want to go over is height. So height is done by uh, height is calculated by starting at the bottom pretty much, and then we will go up until um so so the height of 7. So let's say we're looking at 7, right? The height of 7 is 1, and the height of 5 is 0, and the height of 11 is 2. And how we usually look at height is that height, we usually only ask that if there is a height of a tree. So the height of the tree is always the maximum height. So in this case, it would either be we look at node 10 or 8. So 0, 1, 2. Okay. So the height of this tree is 3. And usually, you can either look at the actual nodes and start at like 0, or you can count like how many or you can count how many arrows there are, right? So both of those indicate a height of 30. Well, depth is pretty much the opposite. So height start at the bottom and you go to the top and then you can count like, I don't know, the arrows or something. Well, for depth, so depth is the other one. Depth, you start at the top and you go to the bottom until where you see the node, and then you can also count the arrows or the node. Okay, so the depth, right? So we will look at this is 0. So we start at the top, then we go to the next one, so that's 1. And these are both 2, and this is 1, this is 2. Okay, so if we were asked like how many nodes have 2 depth, it would be 3, right? So it would be these 3. So let me see. All right, let's go on to the next one. So like I said earlier, that binary search tree is mainly used for searching. And the reason why they're so good at searching is because at each step, you pretty much you try to have every your total amount of things that you need to check. So imagine if you need to check n things, but if it's ordered in such a way that it's kind of sorted already, then we can just cut it in half. So our next bridge will be n over 2. So and then it keeps like breaking down. So n over 4, and then uh you got it. So that's a divide and conquer method. So that's just like type of programming. And then not all binary search trees are balanced. So there is a concept called balanced and unbalanced, and we'll go over that a little bit later. But usually the average time complexity is O of log n. So that is because since it's ordered in such a way that you can't just insert the node anywhere, right? So you always have to insert it where you think it's right. And usually that means that you have to check the root node, and then you'll probably have to check either left or right, with which one you go, left or right. And then you check if what's it called? If it says 2 children, you need to go left or right or more. And then or you can find out that okay, this is good, so you can just add the new node right here. So this would be your new node. And then that's usually a time complexity of log n, because you cutting the each time you do an iteration to insert, you're cutting the amount in half. So like n over 2, and then from here it's like n over 4, and you just keep going down. So you only have to check pretty much log n of nodes. And then deletion. Deletion varies on essentially where you delete it, because a node can have one child, two children, or no children. So there's not a very average time complexity, just because so like no children would mean it's a leaf node, would mean it can like pretty much um it can just be taken out pretty fast. But the one child or two child, you'd have to rearrange the children after you delete them. Okay, and this is the balancing concept. So the balancing concept is pretty much based on one thing. It's it's to calculate the balancing concept, we use depth. So depth is honestly really more important than height usually. Height is usually the attribute of like for the tree, but this one is the depth is like more important for actually calculating the balance. So like I said earlier, the depth starts from the top and goes to the bottom. So what that means is that count the depth. So it's usually, so we want to do left minus right. And then we have to make sure that is between 1 and -1. So that is usually the case. So let's say we're looking at 2, and we want to see the depth. We want to see the like I guess balance variation of two. I don't know the actual like term for it. So 0, 1, and 1. So we see on the left side, the 2 has a depth of 1, and the right side 2 has a depth of 1. Well, if we go at 2 on the other graph that's not balanced, we'll have 2, right? So 2 has no children here, so 0, and then so this is the left side 0. But then it has 0, 1, 2, 3. So it has a depth of 3. So 0 minus 3 is equal to -3. So that's obviously not balanced. There are different ways, there's different techniques to balance it. So AVO trees and red black trees, but you guys won't be really going over them um for this class. I believe it will be okay, so they're saying they're motivating for rotation. So I'm not sure if you'll need it, but we do go over it. So just keep that in mind. Okay. So this is the rotations. Um Essentially there are 4 cases, and this is for AVO trees. So AVO trees are not the same as red black trees, and they each have their own each have their own kind of like specialty. So for AVO trees, you do rotation by replacing. So whenever you see this like right curve, right? But what we're doing is we're gonna take this right curve means that we're gonna take this node and we're gonna replace it with that node, and then we're gonna move this node down. So what's happening here is D replaced F. So now D is the root, and then D, and then F rotated right down to his to D's children, to D's child. So essentially what happens, why we do that is because we see that if we do the depth calculation on this, we see B will be equal to 0, D will be equal to 1, because that's left minus right. Right minus left, I don't think it matters. And then for F, there's an issue here. So for F, as soon as you see that one is the balance is not less than or greater than 1, so if it's outside of that range, then we will we will rotate the AVO tree. So for F, it's I think for this one, yeah, so the 2 minus 0 means equal to 2, which is not less than or equal to 1. So so now we know we need to rotate it. And how we rotate it is these 4 cases. So if you see the left right case, that honestly, like when you do the left right case, it will turn into the left left case. And then once you do know the left left case, you can balance it. So the left right case and the right left case rely on the left left case and right right case to complete it. So the left right case takes 2 steps, and then these take 1 step. And for the left right case, we see this arrow just like we did before. So we see a left arrow, right? And we see that D right now. So we see the left arrow, and we see that the child is D. So what we need to do is we need to replace D. We need to replace B with D, and then we need to rotate B over. So what that looks like is that this. So we replace B with D, and then we rotate it down. Okay, so that's the exact same with the right left, so I don't think I need to go over that. And then we'll talk about traversals. So the important thing about traversals is that they're each used for different things, and they're honestly pretty important to like understand. So in order traversal means that you're gonna go start from the left So you would go all the way far left, start here, and then you essentially go up, down. And if you can't really visualize it, I'll show a method later to how to like do that much easier to recognize, but recognize what it's saying. So you traverse the left subtree, visit the root, and then visit the right subtree. So what that's saying is go left until you can't go left anymore. And then you'll visit the root, and then you'll say, so once you go left, you print out one, and then it says visit the root. That means we need to go back up and we print out two. And then we'll go right again. And then we'll print out 30. And then now because we can't go right anymore, because 30 is the last one, we need to go back up. So we need to visit the root. So that'll be 4. And then we'll go right because we already went left earlier. We'll go at 5. And then this will keep going until it gets to the end, and it'll just be 1, 2, 3, 4, 5, 6, 7. Okay. So this is actually pretty important. So if you see this, it's a really easy way to recognize them is left, print, right. So essentially that means is go left, print it, and then go back up, and then go and then so that's kind of how it works. You'll understand the left, print, right a little more when we go to the next one. Okay, now this is just a real word application. It's essentially just saying that binary search trees are usually done with dictionaries because dictionaries have like each individual word here, they look for like the matching letters, and the matching letters in here would be so the first one would be T, and now we have T and T, and then we see that we have a new subgroup, so R. So R will be a new subgroup, and then TY will be the new subgroup. So everything, all the descendants of um of this tree will have T in it, and all the descendants of this tree will have TR in it, and all the descendants of this tree will have TY in it. So that's kind of how it goes. That's how they break down each letter. And then, so let's go next. Okay, pre-order. So pre-order, we're gonna visit the root, and then we're going to the left, and we're going to the right. So what we want to see here is left, right. Okay. And then I'll show you a method later, so I won't go over this too much. So we'll go down, and then we'll see post order. So post order, this is left, right, and then print. So visit the root is usually like print. It's kind of like the same thing, but I know we talked about post order earlier with like prefixes and stuff and postfixes. So it's very similar to that. So here, if I'll show you an example here, and so we want to visit the left subtree. Where's the left? Where's the left? So let's start at 5 because there's no right subtree, and then we're gonna print it. So we're gonna print 5, and then we're gonna go back up, and then we're gonna see 8, and then we're gonna see that 8 has no right, so print 8, and then we're gonna print 12, or sorry, we're gonna print 13 because we visit the root, and then we see that we've already been to the left subtree, so we need to go to the right subtree, and then we print this, and then we'll print this, and then we'll go back up, and then we're gonna go here, and then here. So if it doesn't make sense, I'll show you a method later that I've been talking about, but yeah. This is just a basic binary search tree, and then this is kind of usually how it goes. This is like the actual algorithm for it. So I don't think it's not that much. Okay, So for, I believe your LE, you're implementing a binary search tree, and then you have to do a insertion with a particular key. So that particular key will probably be the method that you're gonna sort your nodes in. So like you can always add in a particular key that doesn't necessarily um I guess it does, it has to be it has to relate to the data still. But yes. So we'll have insertion. So imagine, remember what we said earlier, insertion is usually log n, because if you have a node like this, you have to check every subtree, and then but each time you omit the other half. So if it's on the left, then you know that you won't need this part. And if it's on the right, you know we won't need this part. And then you have to check if it has two children, one children. Usually that doesn't usually that's not like a case, but usually you want to check for if there's no children. So no children usually means it's a leaf. That means that you can't go any further down. Okay. And then the delete node, you'll probably have to read more about that. And then find. So the find is literally should just be binary search tree. So that should be pretty obvious. Um, and usually I believe you can do that recursively. And then min value. So min value is like pretty simple because the way it's structured, the way the binary search tree is structured is that the minimum value should always be the far left node. So this should always be the minimum value, if that makes sense. And then print in order. So that means you'll probably have to use in order traversal to print true. Okay, so you'll probably have to think a little bit more about in order traversal, but I'll give you a hint where you should follow these steps: left, right, and print, or left, print, and then right. So just follow, probably if you can follow these steps, then you'll realize how simple it is. And then I'll show you a method to kind of like grasp the traversals really easy. So we'll start with 8, 5, 6, 3, 4, 2. I'm not putting them in any particular order. Just like putting down them. So 2, 9. Okay. So the method that you can use to do all 30 posts pre and in order is that imagine you have a dot on every single node. So every single node will have a dot, and then the dots will represent. Well, I'll show you what the dots mean, but we'll have a left dot, a right dot, and then a bottom dot. So imagine you trace the outline of this tree. Okay. Oh, me. Let me move some stuff so it doesn't get confusing. But yeah, when you're setting up these dots, I will say that you might want to like try like make it as clear as possible because like it gets kind of cluttered sometimes. But okay, so we want to trace the tree. and you want to go like this. Okay. Okay. And if we trace the tree, as soon as you hit the dot, then you should write down. So this is we'll do pre, and then so on the first actually but so pre order. So on the first hit, we'll hit 8. So as soon as you hit the dot, you should write it down. So 8, and then we'll go 5, and then we'll go 3, and then we'll go 2. Oh, I should. Okay. So we're tracing it. We go to 3, and then we'll hit 4, 6, 10, 9, 17, 20, and then there's no more red dots, right? So what did I say? So from 2, we hit 4, then we hit 6, then we hit 9, or then we hit 10, and then we hit 9, 17, and so it's really important where you put these dots and you don't mess them up. Because if you mess them up, it's like really hard to like fix it. Yeah. Erase that. Okay. So let's try in order. In order. Start from the top. And we hit 2 first, and we hit 3, and then hit 4, 5, 6, 8, 9, 10, 17, 20. Okay. So what that looks like is so we hit 2 first, and then we hit 3, and then we hit 4, and then we hit 5, and then we hit 6, and then we hit 8, 9, 10, 17, 20. Okay. Make sure you like, especially corners like this area, make sure you always trace the outline of like around here, and then go up and then around here. Okay. It's really important that you do that for this method, or else you won't get the right result. And then we'll do the exact same thing for post order. So we hit 2, 4, 6, 8, 9, 20. Okay. So post order, we hit 2, and then we hit 4, and we hit 3, 6, and we hit 5, and then we hit 9, 20, 17, 10, 8. Okay, so that's pretty much the method. That's the whole method. It's pretty simple. This is mainly for like if you get a question and then you like want to solve it, but this is not usually how you code it. So when you code it, I would follow these steps where I put it earlier up here. I put left, right, print, right, left, print, and then the rest. So that's pretty much all I have to like the review, at least for this. I don't know if there's anything else I should essentially talk about. I think I covered almost everything I wanted, and then I'll show you like so I have a cheat sheet that I made during for class, and I took one to 21, and this is pretty much what it looks like. So I use the same method you see here down here at the bottom with the tracing, and then you can see that I also have a left print right, left right print, and then print left right. So these are also like most cases. that we want to look at. So in order is usually used to print the tree. Post order is usually used to deconstruct the tree, and then pre order is usually used to copy the tree. So yeah, I don't really have anything else. You can see like the operations and stuff, and B means balance. So yeah, okay. I think that'll be it for this recording. Thank you so much.